Good afternoon, everybody. Hope you've enjoyed the day thus far. Had a great morning and good lunch and a good afternoon. And I'm very pleased to bring together a very good panel on taking RISC-V into high-performance systems. Joined here with Steve Wanless. Steve is with Red Hat. Jeff Law. Jeff is from Google. And Amber, sorry.
We haven't swapped yet.
Jeff from Qualcomm and Amber Huffman from Google Cloud, right? And so I thought maybe just to start, if you each want to give a quick little introduction of yourself and your company's interest and investments into RISC-V, to what you could say on that.
Start off with me? Sure. So good afternoon. Great to be here. Really happy to support Andy's in this event. So my name's Steve Wanless. That's written as if I'm someone who doesn't have a wide area network, which has caused much mirth amongst journalists that have interviewed me in the past. I'm at Red Hat, and the role that I have at Red Hat is that essentially I'm the lead of the project that's putting Red Hat Enterprise Linux and all of the tool chains on top of Red Hat Enterprise Linux onto a RISC-V platform. So that's a project that's been running, I would say, for the last 3 years, and continues to grow as the hardware basis for RISC-V continues to evolve.
Jeff Law. I'm with Qualcomm. I came in through the Ventana acquisition about 4 months ago. Not surprisingly, Qualcomm acquired Ventana to develop RISC-V systems. I particularly specialize in the RISC-V software ecosystem and compilers, debuggers, linkers, loaders, all that low-level stuff that just has to work. Prior to Ventana and Qualcomm, I actually spent 27 years at Red Hat, but Steve and I never overlapped in my time at Red Hat. So, Amber?
Amber Huffman. I'm with Google Cloud. At Google Cloud, I'm responsible for our ecosystems, leading ecosystems and standards for Google Cloud. In terms of RISC-V, Google's been very active at RISC-V International, where we serve on the board. My colleague Lars Bergstrom, in the Android side of our business, he serves on the RISC-V board, and then I'm the chair of the RISC-V software ecosystem project to try to build out the software ecosystem. So it's been a pleasure to work with the RISC-V community over the past 3 or 4 years.
Great, well thank you. Thanks for all of you for joining us this afternoon. I should mention there are a couple of microphones around, so we'd like to make this as beneficial and interesting to the audience as possible. So we're not going to reserve questions to the end. If you have questions throughout the panel, please just raise your hand and somebody will come with a microphone so that you can ask your questions, okay? But to kick things off, RVA 23 was a pretty exciting moment for RISC-V, ratified in 24, named in 23. And since the announcement, Linux, Android, CUDA have all sort of rallied around RVA 23. What does, in your mind, what is the road to a true multi-vendor compatible RISC-V where software bases can be deployed and rely on compatibility? What does that road look like?
Well, it starts with RVA 23. I mean, that provides the baseline architecture that the distros can target, that third-party ISVs can target. Without that, you can't take something built on one system and run it on another. And so, to me, as somebody who has been involved in system bring-ups for 35 years, that base system is the contract. And with that contract in place, it allows these independent software vendors as well as the distros to target a common basic platform. So that is step 0. Now we have to have performant hardware. Right. And that may be a whole separate question, so I'll stop.
One other thing about RVA 23 is that it's visible in the user space. So the baseline for the CPU for RVA 23 contains things like vectorization and crypto, which you're going to expect as an application developer to see inside of the tool chain so that you can take advantage of that. So what that means is that this isn't something that's just constrained to inside of the operating system. As you move from one version of RISC-V into another version of RISC-V with RVA23, you're going to have to provide a user space that supports all those RVA23 features, in order to make it worthwhile to the developers that are using it. But I would say that RVA23 probably represents the baseline of everything that we need for a good server implementation. Whether or not RVA23 becomes the baseline for all RISC-V, I think that only time will tell on that, because there's a whole bunch of silicon that comes with RVA23 that, for instance, if you're building a sensor for some form of industrial process, you're not going to need to implement those inside of your sensor. So I would very much like to see the RISC-V world standardize on something that is useful for building large-scale data center style high-performance servers. I'm just not sure that it's going to meet the needs of the entire community.
And what RVA23 has allowed us to do is, all three of us serve in the RISE project, and that has allowed us to actually engage with upstream software communities of, here is the compiler optimizations or the kernel optimizations or all of those pieces that comply to RVA23. So it's enabled that upstream software work to occur over the last 3 years, and now we're excited for hardware, as Jeff was mentioning.
Yeah. And since you mentioned, compilers and user space, I mean, we've been targeting RVA23 in terms of an extension set for 3, maybe 4 years at this point. Yep. So this is not something that the tool chain is looking at and saying this is new. This is something we have been actively targeting. So it really does bring that standardization forward. I think you've got an interesting point, though, in that there are going to be markets where RVA23 may not be the right choice. As you say, a sensor. Does it really need a full vector unit for a temperature sensor, just to pick on something? Mm-hmm. So the RVA23 profile, at least in my mind, it's more about how do you go into HPC, server, cloud.
Mm-hmm.
Right, yeah. What I'd also say is that the introduction of RVA23 has kind of caused a hiccup in the flow of available hardware coming to the market, because suddenly once the standard was ratified, RVA23 became the new shiny object that everybody wanted but nobody had. And so we've seen the sort of the steady drumbeat of the flow of hardware that we could pick up to begin to implement an operating system on. We've seen that essentially freeze over the last 6 months, as pretty much every single hardware vendor is revising their product to be RVA23 compliant. So while again I'm very much in favor of a standard like RVA23 coming to the market, let's not do it too often, because it brings with it a whole set of delays inside of the supply chain to the rest of the market that is very difficult to get over.
That's kind of interesting, and high performance and high performance silicon came up here. But RVA23, I think, as a baseline, how do you see that? Are there markets where maybe the bleeding edge of performance is less required, and there's markets where it enables things sooner before going into true data center central compute? How do you guys see the market evolution that it brings to bear?
Do you want to pick that up first, Amber?
No.
Give everybody a chance to think about their answer, please.
Sure, I can pick it up first. So RISC-V has been in production silicon for many years at Google and in many of our companies. If we think about security IP, things like Calyptra, there's RISC-V in it. It's not RVA23, so RISC-V has absolutely been shipping production and lots of great stuff. In terms of RVA23 and performance, I mean, there's obviously 2 classes we've been talking about. If we talk about high performance, that's one class we'll get to, but I think, Mark, you've also been asking on Android. Mm-hmm. So in these marketplaces, I think you're looking at how do you start with a bounded software surface. And so if I think about Android, what are the likely Android customers potentially going to bring to market first? It's with a more bounded software surface like a wearable or a TV versus, say, a phone. If you think about in data center, you know, it's very interesting with the NASA collaboration and what we see with HPC. That is a more bounded software environment versus if you think about a cloud offering and all of that software that you need to tackle. So I think that's the way we'll see it evolve of where more contained, you're seeing a lot of RISC-V in say, NICs and whatnot. And so that's how that all builds toward this evolution of it being everywhere, but you have to pick your software surfaces to go upgrade.
Yeah. And you know, if we look at, you know, the question you didn't ask is RVA23 sufficient to go into the HPC space?
That's a great question, so feel free.
Yeah, and I guess I'll touch on that. So first, a little bit of background. I've done every RISC architecture. I've done compilers for every RISC architecture that's hit the mainstream for the last maybe 35 years. I don't see anything in RVA23 or missing from RISC-V with the RVA23 profile that would prevent us from going into an HPC market. As far as an ICE is concerned, all the pieces are there. What we really need now is performant microarchitecture. Okay. So all the building blocks are there, we just have to get real performant hardware.
How about at the platform level specifications, right? RVA23 doesn't really tackle that part of it yet.
It doesn't, but it is included in the server platform specification profile, which I think, is it frozen or ratified now?
It's frozen now.
Okay, it's frozen, which means it should be ratified soon. And I believe there may be an announcement coming at RVI Europe around that. Okay. So anyway, point being is there will be a server reference platform specification imminently.
And that server reference platform is going to be really useful to everybody here. If you're using RISC-V in some form of development capacity, because I would say to you, if you now sit here and think to yourself, the last time that I put Linux on a RISC-V platform, I did what? You probably had to go and find the flavor of Linux that you like, that you were going to put on that platform. And you had to go through that distribution's download page looking for the image file for that specific piece of hardware for you now to download and put onto a flash drive that you were going to insert into the board that you wanted to boot Linux up on and get it running in that way. And you just had to keep your fingers crossed that image was going to support everything that was on your board. And one of the things that I am very much looking forward to with that new specification that we're making, that we're talking about here, is that with it will come support for ACPI boot protocols, ACPI 6, which means, yay, the industry might be able to produce an ISO file that you can use to boot Linux on a range of different hardware.
Any hardware that implements the specification.
Which would be an absolutely wonderful thing. But to come back to Mark's earlier question, let me be controversial and say the market for high-performance RISC-V machinery already exists. And right now, the world cannot get enough of platforms to run artificial intelligence workloads on. I would say to you that very probably the easiest path for enterprise-level RISC-V devices into the data center is going to be as a platform to run artificial intelligence workloads. If you take a high-performance RISC-V machine, you layer onto it an operating system and one of a number of different tools in the industry, like PyTorch, for example. On top of PyTorch, you can then host LLMs of your desire. But in that software stack that I've just described, there's very, very little legacy software. And in the past, it's been reams and reams of legacy software that have prevented the rapid adoption of new instruction sets. And what I would say is that for RISC-V, the market's already there. And RISC-V has an advantage of going to market with that set of workloads that I don't think any other instruction set architecture has had such a good opportunity on in the past. I mean, I've heard software vendors talk about it takes 10 years to get full support of an instruction set architecture up into the software environment. I think RISC-V has got the potential to do that very, very quickly, just on the back of the seemingly endless requirement for supporting artificial intelligence and machine learning environments.
Although to your point, Steve, about AI is changing the game, it absolutely is. I'd say it is changing the game about how long it takes for software to be ported. And so Google released a paper in October last year talking about our journey from one ISA to multi-ISA, and talked about a lot of it wasn't so much porting the code, but it was the using AI and automation to be able to, a lot of it was build files and other issues in linking and whatnot. And so with, AI models have only become better since that time, and so we see the AI and automation making it such that it's really performant hardware that limits our ambitions, because with software we have these new capabilities for porting and really amplifying and moving much more quickly to get the software in place.
And actually, I would add on to that, if you haven't watched the presentation, and I'm not sure who it was at Google that gave it.
Martin Moss?
Yeah, at RVI North America last year, watch it, it's good.
Well, and it's interesting in the AI domain. We had a number of AI talks this morning focused on how RISC-V is being used in high-performance AI. And those dovetailed into the specialization of workloads, adding custom instructions, which is a little bit on the other side of the spectrum from doing things like standardizing the ISA profile under an RVA-23. So, how do we navigate the two edges of this sword?
So that's a really interesting question in terms of adding instructions to the instruction set inside of a RISC-V device. Because I haven't met a hardware vendor that doesn't think that's a good idea. Right? Because hardware vendors definitely looking for some kind of differentiation of the product, and adding their own custom instructions to the RISC-V instruction set seems like a great idea to differentiate out in the market. The difficulty for the software vendors is the long tail that goes with those incremental instructions, because it means that somebody has got to support the compiler toolchain, the assembler for those instructions, the debugger, the link loader, all of those things that suddenly these new instructions can touch on. And so I would say at Red Hat we've had a real change of heart about this over the last maybe year, because initially we said to those hardware vendors, you're absolutely free to go and create instructions that are not part of the RISC-V instruction set, but don't look at us to actually go implement the software to drive those instructions. So if you want to go do that, absolutely fine. We feel somewhat uncomfortable about it. And I guess we've gone on to the other side of that coin now, that basically says we're going to implement our operating system and everything that sits on top of the operating system to the RISC-V standard, which is why the RVA-23 standard is so important for us. We are not going to touch anybody's custom instructions. If you build different instructions into your silicon, that's down to you. We are certainly not going to extend any of our libraries or tool chains to cope with that. So whether we're going to see a rash of alternative compilers and tool chains out there to support incremental instruction addition to the instruction set, I don't know. What I would say is that gets really expensive really quickly to maintain that level of software.
Yeah, and what I would add on to that is, from a toolchain standpoint, adding new instructions is not hard. That it's well understood. And so if there is an AI specific acceleration instruction that you can plumb into MLIR, that's all possible. What is going to be critically important is that we do what we call dynamic dispatch, which means that if it queries the hardware you're on and says, oh, you have the new fancy instruction, use it. If not, go to your fallback path. And I think that's the model that we're going to have to use for these custom instructions that have significant value in certain stacks. Because the base OS does not want to be aware of those new instructions. It doesn't want to have those built into it because it's not going to run on everybody's hardware.
And that's really the kind of conversation with the hardware engineers, is to say, you're getting 1% by this. Can you enable this with a software stack that you control, or a limited software stack? Great. If you're expecting this whole open source software upstreaming to realize the value, maybe that's not the best idea. So I think that's always a healthy conversation of what software enabling are you expecting for this?
Yep. And that's a conversation I've had with many hardware designers.
Exactly.
Sorry if that didn't go the way you wanted it to.
No, that's
The whole
fine.
panel's not going the way Mark wanted it to.
Well, and if it did,
go
it would not be interesting. So, and just a reminder to the audience, we have a question. Yep.
Let's get a mic over there.
Microphone. You can try that.
And maybe we could
but,
repeat the question.
So somebody at this conference earlier today described the sort of the pain that ARM has gone through in getting software to migrate for ARM in the data center. And it's taken whatever, is it even there? I don't know, 10 years, something like that. But the interesting thing that this person said was that migration was less about ARM and more about not x86. And so that person felt like now that there's the pain of not x86, the incremental pain of going from something else, RISC-V, will be significantly less. And I was sort of curious for the panel, does that ring true to you? Or are there holes in that theory? What do you think?
No, that rings true. That's what this Google paper that in October, and we published a blog on it as well, talking about multi-architecture. Going from 1 to 2 is harder than going from 2 to 3. And obviously, if you already have support for a RISC-style architecture, adding another RISC-style architecture. And if you look at the journey of what the ARM enablement went through to go through server, you did not have the advantage of AI and automation that you have today. And so we should be in a much better place of software not being a 10-year-long pull journey. It's really about getting that performant hardware.
Yeah, I would totally agree. And you know, I was involved in the AR64 bring up at Red Hat, and we started in 2012, if I recall. And it wasn't until maybe 10 years later that Red Hat actually had significant revenue from that product. The RISC-V journey, I believe, is going to be dramatically faster. The problem areas that I see are things like intrinsics. People who have written code using C and C++ using the intrinsics that are available on AR64. And that's where the AI system starts to come into place, because there are, for many of them, fairly direct translations. So you're going to get 80%, 90%. I'm not sure what the number is.
Something large.
Something large. So I don't see it being a 10 or a 12-year cycle. I see it being essentially these huge steps in capability as hardware becomes available.
I would say from the operating system point of view, supporting another instruction set isn't necessarily a big deal. If you look at the number of instruction sets that we've wound up supporting now, we've got support for all the IBM instruction sets, so Power and Z, clearly Intel and AMD. At the moment, we have one operating system that supports both of those x86-based vendors, although I believe that may wind up changing as we get into the more commoditization of where those two instruction sets start to diverge. So, for example, if you were to look at confidential computing, it's another essential piece of technology that's going to get implemented for security on top of operating systems. Both Intel and AMD have got completely different ways of implementing confidential computing. So at some point, I'm guessing that we're going to have to look at different distributions for Intel and AMD. But the number of the number of instruction sets really doesn't matter very much. It's a question of when does support for those instruction sets get to a point where it makes sense for workload adoption on them. And what I'd also say that also might be a little bit controversial is when my management chain says to me, Steve, when are we going to see a profit out of RISC-V as a technology in the market? I've got an awful lot of unpleasant truths for them around this, because essentially what I'm going to say to them is, do you think that RISC-V is going to expand the server marketplace? Do you think there's going to be more servers in the world because of RISC-V? And the answer to that is probably not in the beginning, although I could make a case for it happening over time. And so if RISC-V isn't going to expand the total addressable market of servers, what's going to happen is that as RISC-V gets introduced into the marketplace, what it's going to do is take away market share from other instruction set vendors. And so being a commercial company, the reason that Red Hat has an interest in RISC-V is to make sure that we continue to pull subscription revenue in order for us to continue as a company. And so there's one way of looking at RISC-V as a technology that says, yay, it's great, it's new, it's a new technology that we can use. But the other side of that is that there's got to be a business case that goes with it. And that business case, certainly I think for almost all of us up here on the panel, is that what we're trying to do is to prevent revenue erosion, silent revenue erosion, as the market begins to shift from one instruction set to another.
I think that's a fair way to put it. Position yourself for where the market's going.
Right.
And you did touch, I think, a bit on earlier in your response, confidential compute, which is kind of table stakes in data center, and along with things like RAS, which I think is part of the platform specification. And yeah, but I believe Cove is under discussion
It
or
should
not
be
yet.
going
Is
to
it going through ratification?
freeze really soon.
Okay.
There were some things that were going on in the Cove space that I think that committee wanted to see resolution on, as far as like the market. And then once they saw that, then they can move forward to ratification of that particular extension. So Cove I expect as soon as is Cove IO.
Okay, and I guess, given the nature of the panel here, we've got everything from hyperscaler cloud to silicon and tools into, OS and virtual machine. What's the real lift to go from, let's say we had this super high performance silicon sitting on the table right now. What's the real validation cycle till this thing's actually in a cloud data center where it's usable by the masses?
I think if you think about any type of deployment, you're talking, I've got to get the silicon in, that I can then deliver a board. And then from the time of the board arrival to getting all of the low-level software fully running and all of those things, and you're doing usually, a DVT to a PVT type of boards of cycle of validation, you're usually talking at a minimum a year, but probably more like 18 months to 24 months, right? And it's one thing if it's the first of a new product line, and so that's probably going to be more towards the 2-year cycle. So we're really at that bubble of you need the performant hardware to come in that's a server class solution with, say, 64 cores and 4 gig of memory per core, that type of thing that really gives some a state-of-the-art implementation. And then you can from there, how do you go and get that platform ready, run it through its paces? And the first one is always the fun one, and from there, life goes better. But the confidential compute, it's just software, and it's and with a good implementation, it's just software, Jeff. And Steve, how
No,
hard
it's
can it be?
not. No, it's not.
But
It bleeds out into the SoC significantly.
It does, it does.
But the implementation of the hardware is just the beginning. I mean, because on top of that, what you're trying to do then is get to a point where you can run a service.
Yep.
And so on top of the hardware, there's the operating system. And on top of the operating system is the hypervisor that's going to enable you to create virtual instances for your client base. And then you're going to have to define what does each of those virtual machines actually look like, and what's the application selection that goes with that. Then you're going to get into all number of accountancy and audit trail questions for the actual operation of the service. So the hardware is just the beginning of that story.
But it's the piece that we're most blocked on right now.
It's the piece that's missing.
Right. So once that hardware becomes available, so to come back to your question, let's say that I got a rackable system sitting in front of me. What next? And the next, at least in my mind, is you get it into the data center, and you're going to have these, whether it be a Google or a ByteDance or whomever, they've got their own software stacks.
Yep.
They're going to have to do POCs on that server for their stacks and prove that it has the right performance, prove that it works properly. And then probably the next generation is when it actually goes production. So there's probably 2 steps there.
Right.
At least that's what I'm seeing. I don't know, do you have a different view there, Amber?
I mean, certainly we hope that you can get to production in the first step. Now, maybe that first step is not a million machines. Maybe that's, you're 1,000, you're 5,000, you're 10,000, you're 20,000.
If it was 20,000, I'd be happy.
Exactly. So how do you get that number of machines out there that you really are running through its paces and getting a good profile of what is working well and what needs tuning for where you're going, of really that much broader, and that's what I've seen in other journeys.
Yeah, that's fair.
And I think the industry is still waiting to see a device with a whole bunch of high performance cores on it.
Mm-hmm.
So, there's kind of the elephant in the room here of, the 800-pound gorilla who has stepped into data center CPU domain. And, how do you see this? Is this a no-op in RISC-V? Does it create incentive for RISC-V? How do you see that play out for the impacts on RISC-V going forward?
Well, I think its existence just validates really what I said earlier. The market for RISC-V is already there. And the example that you're giving, Mark, is of a CPU that's been brought to the market to fit into that void that's there right now. I think it's just purely validating that there is a market for high-performance RISC-V CPUs waiting for the hardware vendors to bring them forward. I certainly don't see it as a no-op. From a RISC-V point of view, I actually think it's quite encouraging.
Right.
I would largely agree. If we had performant hardware in the RISC-V ecosystem, it would be ready to rock and compete with that 800-pound gorilla. That hardware is not available yet. But what that says is it's validating the market. The market is there waiting for somebody to come in and bring a high-performance design in that can run those workloads.
I mean, if we go back a year, I think a lot of people were questioning, hey, the CPU, it's kind of boring, GPUs and TPUs and whatever XPU. I think the age of agents that we're now entering into has really validated that CPUs are going to continue to have a very big role to play. We're seeing that. If we look at, we're also seeing at Google a ton of heterogeneity. And so we are seeing, we deploy AMD, we deploy Intel, we deploy ARM silicon, we also deploy TPUs and GPUs and all of these different pieces. And we're only going to get into more heterogeneity as we go. So that validation that CPU markets are super healthy, and can we deliver, I think from a RISC-V perspective, delivering very high performance at low per unit cost or per work cost, however you want to look at that, is a big opportunity that I think RISC-V has a great opportunity to go tackle.
So Mark, if you know anybody who's building RISC-V hardware,
Do we leave
after
today
the
with
show.
performant boards?
Yeah, meet me after the show. I got to stop
I
that.
need my RVA 23 profile board when I leave.
But speaking of performant hardware, and Jeff, I know you're deep in tune with this on the performance side. But is there anything? There's always been the go back to the ISA wars of RISC and CISC, and which RISC ISA is better, and should you do branch windows or no branch windows? When you look at the ISA, is there anything that fundamentally says RISC-V is going to be super good performance, not so super good performance? Is it a don't care?
I think in the end it's a don't care, and I say that having worked on, I've done register windows, I've done Itanium register windows, which are even weirder. I've done so many RISC-V performance efforts. I just don't see anything, or sorry, not RISC-V, RISC performance efforts. I don't see anything particularly missing in the RISC-V ISA. Are there quirks? Certainly, but every design I've ever worked on has quirks. Right. Nothing that we can't cope with from a compiler and library standpoint.
And if you go back to those RISC versus CISC wars of the 90s?
Late 80s, early 90s.
90s, yeah.
I would say that was mostly marketing.
Yeah.
That there really wasn't a great deal of technical differentiation. And to be honest, you could have even looked at, for example, x86 and made a case that an x86 was a RISC processor when you compared it to a VAX 11780 or something like that. But perhaps that's going back too far.
No, not at all. I understand where you're coming from. Yeah. But I think you're right. If you look at the power architecture, if you look at the HPPA architecture, the SPARC architecture, the parallels are MIPS. The parallels are astounding. The differences are small. And what we saw happening from a performance standpoint is whoever had the most recent chip had the best performance. And they just kept leapfrogging each other over and over and over again.
And really the instruction set architecture only makes a great deal of difference to the lives of people that are programming in assembler. Right?
Well, compiler junkies.
Yeah, or compiler junkies. And how many people are programming in assembler nowadays?
Well, and that's the problem with intrinsics. People think that intrinsics are better than assembler, and you see a lot of that.
Right.
And that's somewhat problematical.
So I confess I spent last Christmas reading a book on RISC-V assembler, and I could probably program in it now if there was a decent assembler around. But I think I'm in the minority of that.
You might be.
Yeah.
So it's a lost art.
Let me jump into the assembler and intrinsic discussion here, and take this just a slightly different direction, because the vectors and matrix and the fact that these are scalable and length agnostic. This is proposed to be a very, very big benefit for RISC-V, but I also find it interesting how it exemplifies the standardization process of things. So maybe comment a little bit on what makes RISC-V vectors or matrix so special, and is the standardization process of an open architecture better in any way?
I think that the quick answer to that is that RISC-V vectors are probably the best vector implementation that I've seen in a while, because they don't have a compiled limit on how long the vector can be in order to be able to use the hardware. And so I think that with the vector support in RISC-V, you can go from a 128 length vector to a 512 length vector, and the hardware will just deal with it. And I think that's a huge step forward from other vector units that I've personally programmed in the past.
You want to say something before I jump in?
Go ahead.
Oh, okay. So I've done a number of vector designs. I would probably not choose vector length agnostic if you were to ask me where to go, but that's where RISC-V is. Is it inherently better or worse? The ability to run on hardware of different vector lengths, it's useful. But I would not say I want to run the exact same code on a smart glasses as I would in the data center. That premise, I think, is fundamentally flawed.
Okay.
You're just not going to do that. But the idea of being able to scale your vectors up as you're running on bigger hardware, there's value there. And I've worked with organizations that, so you mentioned 128 to 512, but I was talking to a company that's doing 16 kilobit vectors on RISC-V. And it presents certain problems. But yeah, it's an interesting vector architecture. It has some really interesting properties. From a compiler standpoint, it is what it is. I wouldn't make that choice, but we can manage with it.
Do you think that you're still going to see teams of programmers optimizing code for given vector lengths?
Yes, but particularly in the benchmark space.
And I think this comes back to heterogeneity, right? So you're going to see that for an Android wearable, you're going to want one vector length that's very different than what you want for a cloud offering. And I think it's going to behoove a bit of standardization in each market segment of what are they really after, because to Jeff's point, going and optimizing a different vector length for the same market segment is probably not ideal. And so coming together as a common you could imagine in lots of places we have for this, for cloud, hey, we want this vector length. We also want, from many of the cloud vendors, we want, for example, there's a lot of security stuff that could be optional, but we may want for that segment that you don't need for an Android segment, maybe. Attestation is required, for example. So I think there's an important piece that RVA 23 sets a profile, but then per market segment, I think there's coming together to say this is really the vector length that we think is optimal for this space and other pieces.
Yeah, not only a vector length, but it's usually referred to as a minimum vector length.
Yes, yep. That's fair.
And there may be a day where the sweet spot for a minimum vector length moves from 128 to 256 or 512. Right now, it is still 128, and it's a really nice sweet spot. 256 is doable. 512, it's hard to do from a compiler standpoint. It's just hard to find enough vector code to run at 512-bit vector length.
Okay. And I've just got to keep a little bit of an eye on the clock here. So before we ask the closing question, I did want to open up again to the audience.
Hi, Ian Cuttress, More Than More. The conversation about about data center CPUs is interesting because you've got Amazon with Graviton, Google with Axion, Cobalt as well exist. All these hyperscaler companies have pivoted towards ARM in some form or another, especially for a lot of their back-end workflows. And a comment really, we just saw NVIDIA invest $5 billion into Intel. And every analyst I speak to is of the opinion that that's because nobody wants their Vera CPU. They want an x86 one to go into their NVL72 racks because they want to go back to x86. They're fed up of trying to program on an ARM system at data center scale for their AI. So if I was being facetious, I'd say, does that negate everything you said about RISC-V in the data center? But I'd love to hear your thoughts on that being the reality right now.
I truly don't see the world continuing to coalesce around x86 as its chosen architecture in the data center. I think that's something that's come about purely through history. I think that if an architecture like RISC-V can demonstrate its advantages, it will get picked up. So I'm not necessarily sure that I agree with your point of view there.
Well, and it may be that there's going to be different performance, price, power. There's a curve there, and depending on where you want to be on that curve, you may choose a different architecture. So I don't think it's black and white.
I think it still comes back to heterogeneity. I can't really speak to NVIDIA's product line, but certainly some people may want a head node that's x86 because that's what their investment of the rest of their stack is in, and some people may be willing to go to an ARM head node. So there's that whole piece of things, but like from a Google perspective, we're offering AMD, Intel, ARM, and the heterogeneity and offering choice is going to continue to be something that I see in the future.
Thank you.
Is Sally here today? Okay.
Aw.
Another question?
Yeah, so Jeff, you mentioned the microphone. So you said vector length 512 is hard for compiler. Can you explain why?
Just finding enough data to keep a 512-bit wide vector filled is hard. It just is. If you look at C and C++ code, it's not really amenable to vectorization often. And it's a lot easier to fill a 128-bit wide vector than a 512-bit wide vector. It's just a matter of finding enough parallelism. It's just hard.
For AI, it's a different story. So easily you feel.
So that's a different space. So if you're in the AI space, you're going through the MLIR path, and you're doing machine lowering out of MLIR, that is going to be a lot easier to find big vector capabilities. And that's why, so I mentioned I have worked with a company that was doing a 16 kilobit vector. It's for AI.
Any other questions? Come on, don't be shy. All right.
Hi, Olaf Johansson, unaffiliated. Software engineering and enablement of hardware has drastically changed in the last 6 months with agentic coding, people not even having to look at the code that gets produced and all that. How do you see that reflect on things like enabling new architecture and making sure RISC-V is enabled everywhere?
I'm sorry, could you?
I didn't catch the end of that.
Yeah, could you
How
repeat that?
much agentic coding and sort of the development in software engineering and the way software engineering is changing right now, how is that affecting RISC-V and enabling RISC-V, for example, to catch up with ARM?
I think Amber actually goes right back to what you guys were doing at Google.
Yeah, I think that the paper we published in October is just foreshadowing what we'll only see accelerate. And so the AI and automation allowing you to more quickly port code and have that flexibility really allows you to, what would have looked like too insurmountable to tackle because of the amount of SWE hours it would have taken to port particular code, is something that you can imagine doing it very quickly. And agents seem to be quite good at porting different code. I get numerous anecdotes of people of, hey, I had this code in Go, but I needed it to be in Rust. One of our engineers was like, I didn't know Rust, and so I learned enough Rust to be able to check what it said, and I let it just,
Do its thing.
So you've got one engineer that can take something in a particular language and move it over, and so yeah, it's Olaf, it's absolutely gonna expand, accelerate what can happen.
Well, that kind of translation from one language to another. I had an engineer that was dealing with Ruby.
Yep.
And it's like, and I need it in Python. All right, fine. Let the agentic things run with that, and half an hour later, out popped a Python script to do what the Ruby script was doing.
Yeah, and you probably have some touch-ups to do, but it's
I don't know.
95% there, or maybe not.
Depending on the problem. Like some problems, I'm willing to let it go. So if it's throwaway code, if it's a little bit of analysis code, I'll just let it do its thing. And as long as I get something out the back end that looks sensible, great. I don't use it to write code for the compiler itself. It's usually analysis scripts, that kind of stuff.
And I think that comes back to, I think we're going to undergo a change in software engineering of really how is one of my colleagues at Google is very much espousing design is the new code. If you've got the AI generating your code, a lot of your design in the past was embedded in comments. Mm-hmm. Really, you have to structure out of how are you having a conversation with the AI about, hey, this is the design I want to build. Ask me questions to build a really robust design and use. Many people would point out that AI can be sycophantic, but instead if you say, hey, your job and the greatest help you can be to me is to ask me questions to ensure I have a robust design, utilize that of prodding it into asking those questions, also then developing, hey, now I want you to help me build a verification plan and what files can you touch exactly. So a lot of this also comes to how do we change software engineering practice to utilize these tools as craftspeople versus as toys, because you're not going to get great outcomes with one-shotting. And so how do we just re-engineer our software engineering practices as well?
Well, that's going to be I suspect, a major focus at the university and beyond level.
Absolutely.
For the next N decades.
Yes.
So I think the net is that it's going to improve RISC-V's penetration primarily because all of those pieces of software that I have alluded to previously that are legacy code will move over to a RISC-V stack very, very quickly indeed. The fact that Claude can now program in COBOL is terrifying.
Okay, we're running a little bit over time, but we'll have time for maybe one more question if there is one. Because I get to close out next, so I'll just eat it out of my time. Got a question right there.
So I think, Jeff, you mentioned MLIR. So what needs to be done in MLIR to support RISC-V?
So MLIR for RISC-V is already up and functional. So what you're really looking at is lowering from MLIR to your target capabilities. So if you have a matrix multiply instruction, what are the parameters that takes? What are the kind of types it takes? So it's really about lowering to a particular implementation's accelerated operations. So to give you to be more concrete, in the VT2 design, we had an innate multiplier, matrix multiplier. We can lower to that in MLIR, generate an innate matrix multiply, ship it over a transport, and run it on an emulator. Does that answer your question? Okay.
Let me ask just one closing question of everyone. And if you could change one decision, a priority, a behavior across the RISC-V ecosystem right now, what would you want to change in the RISC-V ecosystem today?
Hardware availability.
Told you I'll sell you some out back.
Okay. Hardware availability.
Yeah, I would totally agree with that.
It's been finding hardware to build on has been the hardest thing for the project that I'm running. If you watch what Red Hat do, you probably noticed that we put out a developer's preview of Red Hat Enterprise Linux on a RISC-V platform. We did that last year when we announced a new version of Red Hat Enterprise Linux. That was version 10. To give you an idea of the speed of the hardware, it takes nearly a week to compile the C compiler tool chain.
That's a P550.
On that system, yeah.
And you know, as somebody who does GCC work, standard procedure for GCC when you bootstrap the compiler and then you run the test suite. On the Banana Pi K1s, it's about 29 hours. To put that in perspective, on my high-end Skylake, which is getting pretty long in the tooth, that's an hour and a half. So we've got it. That's the gap that's got to get closed. And so what would I change? Getting better performant hardware in the market, even if it's not going to be high volume, to enable that market to continue to move, the software ecosystem to continue to move forward.
Yeah, and that's one of the key things we're trying to build out with seeding the RISE build farm in Q2 and building out more boards is how do we give developers access to that more performant hardware as it comes. So completely agree on performant hardware, and I guess the only other thing I would throw out is patience and persistence, right? We've got, as Steve mentioned earlier, RVA 23 kind of developed this hiccup of, okay, now we need hardware that complies with RVA 23. We need to continue the good software work that groups like RISE and a lot of developers are doing, and be ready when that hardware shows up.
Yep.
Unfortunately, some of us work for companies who say things like, "What have you done for me lately?"
Yeah. Yep.
Okay. Well, I want to personally thank all of you for some traveling quite far to be here and join us today, and a great panel. So ask you all to give a round of applause to our panel.
Thank you.
Thank you.
Thank you.